Hey, good afternoon, everyone. My name is NITheCS Colloquium. I'm part of the NITheCS Associate, mainly on quantitative finance. But today it gives me a great pleasure to welcome Professor Francesco Petruccione, who is going to talk to us about a century of quantitative or quantum from foundational to the futures. I want to introduce you formally. Professor Francesco is our NITheCS director, and he has an outstanding career. He is a physicist by profession. He has a PhD from the University of Freiburg, and he has a career spanning in quantum science, computational thinking, and also artificial intelligence. After finishing his PhD from Freiburg, he got a position at the University of KwaZulu-Natal, where he was a chair for the quantum information processing and also served as a Prof chancellor for big data and informatics. So, like I said, there's a lot of accolades accompanying Professor Francesco. He is a Google Scholar of Citation, about 30 or more than 30,000 citation on his Google Scholar. And he is also recently was awarded a SER from the Italian for the most contribution in his academic work. So, Professor Francesco, we are very honored today to have you, especially to talk to us about what happened in the quantum sciences. And today we're looking forward to learn from you. And you set a good example to teach us about the foundations of these quantum sciences. Over to you, Prof.
Thank you very much, Mesias, for the very kind introduction, and good afternoon, everyone. So last week was the official opening in Paris at UNESCO of the International Year of Quantum Science and Technology, and I was there. And originally we had planned for today another talk, but since the speaker could make it, I thought it's a wonderful opportunity to officially launch the International Year of Quantum Science and Technology in Stellenbosch and in South Africa as well. Yeah. Sorry, now I don't remember how this works. Sorry, now I went too fast. Sorry, I need to go one back. So, what is the International Year of Quantum Science? 2 years ago, 1 year ago, the United Nations officially declared the International Year of Quantum Science and Technology, and it was supported by 70 countries, yeah, representing 5 billion people. So today is one opportunity to reach the 3 billion that officially didn't support the International Year of Quantum Science and Technology. Yeah? So the mission, this is out of the official website of International Quantum Year. Yeah, is that no one owns quantum science. Everyone is invited to join quantum science and technology. We should recognize consensus, honor dissent, admit ignorance. Yeah? Will go down well in the United States at the moment. Yeah? Help others find reliable quantum information. Try to conduct ourselves in an ideal scientific manner, be honest, and above all, have fun. Yeah? Again, on the website of the IYQ 2025, some of the quantum achievements are listed, yeah, from health and well-being to clean energy. Quantum technology is everywhere. Yeah, I won't read it. You can browse on the website. Yeah. But what I will share with you today is is essentially these five chapters. Yeah, I want first to start by reviewing a little bit the historical origin of anything quantum. Then I will spend some time remind you of the birth of quantum mechanics 100 years ago, 1925. The relevant works were made. Then I will show you some advancement of the so-called first quantum revolution and finish with the second quantum revolution that we are experiencing now, yeah, and conclude with some random remarks that might be interesting or not. We will see. So let's start with chapter 1, the atomistic view and early quantum ideas. Yeah? The idea of atoms started probably 2,500 years ago probably even longer. Yeah, people like Leucippus came up with the idea just by thinking about it that reality consists of atom and the void. Yeah, so it's already very interesting that he understood that nothing can exist without void. Yeah, empty space is also necessary. Yeah, so that was 2,500 years ago. Yeah, but he had a very causal and deterministic view of how these atoms are supposed to move. Yeah, and so on and so forth. Yeah? The tradition continued with Democritus, who was his his student. Yeah, and and he stated very nicely, atoms and the vacuum were the beginning of the universe, and that everything else existed only in opinion. That's it. Yeah. So that's quite nice. Yeah. And he sometimes attributed as to be the one of the fathers of materialism. Yeah. Everything is composed by atom, and there are atoms of different size and shape, and this diversity leads to the diversity in in matter. Yeah? This continues with other people kept evolving this idea. For instance, a famous one is Epicurus. Yeah, now we are 270 before Christ. Yeah, and he just developed the idea of Democritus and Leucippus, and he introduced something absolutely interesting. Yeah, that the Greek called klinamen, but essentially is randomness. Yeah? He introduced the idea that atoms move around, mainly deterministically, but every now and then something random happens. Yeah? And that is because he needed something to contribute to the idea of free will. If everything is deterministic, there is not much free will around. Yeah? Interestingly, and this I learned only on the weekend, yeah? Even in the Indian tradition, yeah, 600 years before Christ, yeah, the idea of atoms arose. Yeah, this gentleman called Kanada, yeah, who wrote in Sanskrit, but on Wikipedia you can read everything about it. Yeah, and he went even a little bit further. Yeah? He said there are 4 classes of atoms. Yeah, interesting, it's earth, water, light, and air, not fire. I don't know why. Yeah? But anyway, and and the very interesting thing is that he had an idea that symmetry and invariances plays a role. Yeah. So he said atoms exist, but they're spherical. Yeah, that's wonderful. Yeah, that's really very nice. Yeah. And then something terrible happened. Yeah. Sorry, did I jump too far? Yeah. Then something terrible happened. Aristotle came on the scene. Yeah. and he didn't like the idea of infinitely divisible. Everything was continuous and smooth. Yeah. And not only that, he also didn't like the idea of the randomness. Yeah? Everything needed to have a purpose. Yeah? And this was, of course, what was picked up by the Christian Catholic philosophy or theology of the time. Yeah? And of course, people like Thomas of Aquinas thought atomism is a heretical idea. Yeah? So put them on the fire, end of story. Yeah? So essentially, for 1,500 years, atomism was dead. Yeah. And then again, one religious guy that you might know or not, Pierre Gassendi. Yeah, he thought, okay, maybe it was not so stupid. Yeah, let's propose that atoms were created by God. Yeah, and all of a sudden it was again a good idea. Yeah, that's quite interesting how things can change very quickly. Yeah, and he was of great influence for Galileo, Descartes, and Newton. Yeah. Without him making atoms again acceptable in a religious manner, Galileo, Descartes, and Newton would have had a very hard life. Yeah? Newton picked up the idea in his corpuscular theory of light. Yeah? And in his treatise on light, he managed to explain things like reflection, refraction in his particle corpuscular model of light. Yeah. Then, of course, there was a little bit of trouble with Huygens, who proved that light is a wave. Yeah, but this is okay because, as we know, there is always a little bit of duality between particle and wave. Yeah, so this was very nice. A little bit later, some people claim the discoverer of the atomic theory, yeah, John Darwin in Manchester, yeah, he started essentially setting the basis for kinetic theory. Yeah, he realized that you could explain things like pressure and things like that by collision of atoms expanding in a in a gas and so on and so forth. And he also realized that atoms of different kinds form chemical elements. And when you have chemical reaction, it's not like elements are born out of nowhere. They just combine and recombine without being created or distracted. Yeah? And this is really the first time that something quantitative in the modern theist world of, of quantum theory appeared. Yeah? Sorry. Yeah, let's move on to chapter 2, the birth of quantum mechanics. Yeah? Now we jump to the beginning of the 19th century and effectively to 1900. Yeah? And people like Max Planck discovered, were forced to think about a problem, yeah? Something that was called, or is still called, the ultraviolet catastrophe. Yeah? That classical physics is not able to express, to explain how the spectrum, the intensity of the spectrum of a black body behaves at low wavelengths. Yeah? In the classical theory, which is the red line, it just explodes. Yeah? So, and he was forced to introduce the so-called Planck constant. Yeah, this h that is obviously very small, 10 to the minus 34. Yeah, it's a small number, but it was for him not something real. It was more a mathematical subtlety. Yeah, you introduce this unit of small constant. Energy is just in units of multiplies of this small these small quanta. Yeah? And it was not a dynamical theory. It was just a static theory that just described the spectrum of black bodies. Yeah, and this led to him winning in 1918 the Nobel Prize. Yeah? A few years later, 1905, Einstein solved another puzzle. Yeah? In the famous year in which he published also the paper on special relativity and so on. Yeah? And the puzzle was the classical observation that by irradiating metals with light, people observed that there was a critical frequency that was needed in order for electrons to be kicked out. Yeah? And people thought that by just increasing the intensity, it would work, but it didn't. Yeah. And again, he developed this theory for the photoelectric effect, essentially by assuming, by setting up the hypothesis that the energy of light is also quantized. Yeah, and again, the Planck constant plays a role. And this is the the publication that led to his Nobel Prize, yeah, in 1921, because yeah, and not his work on that. All his other papers are his services to theoretical physics. Yeah? But anyway, this is the paper that led to his to his Nobel Prize. Yeah? But this again is just, you know, the role of quantization now in the case of light. Yeah? In an atomistic model description, the first serious attempt was made by Bohr, yeah, in 1913. And his idea was that the orbits of electrons around a nucleus are quantized. That there is a condition that quantizes essentially the momentum of the electron circling the nucleus. Yeah, he had this picture in mind. Yeah? And this was necessary because in the old model of Rutherford, yeah, if electrons just spin on a circle, they radiate so much energy and fall in the nucleus. Yeah? So this doesn't work. Yeah? And with this trick of the quantization of the momentum, he managed to predict what it was called the Balmer series for the spectrum of the hydrogen atom. Yeah? So this was very nice. Unfortunately, it worked only for atoms that have more or less the structure of the hydrogen atom and not for more complex molecules or other atoms. But this was enough to give him the 1922 Nobel Prize. Very interesting step. And we are slowly getting to 1925. Yeah? Was de Broglie, yeah, in 1924. he wondered, if photons behave like waves and particle, why does not matter also maybe behave like wave? Yeah. And he came up with this famous formula, putting in relationship the momentum of a particle with the wavelength of the particle, of the wave corresponding to the particle. Yeah? Again, age plays a role. Yeah? And he was very lucky because just 3 years later, these gentlemen, Germer and Davison, made an experiment and proved his theory. So 3 years later, 2 years later, he got then eventually his Nobel Prize for the discovery of the wave nature of electrons. So now, next step, 1925. And this is the reason, this and the next slide are the reason why we celebrate the International Quantum Year of Science this year. Heisenberg was sick, suffered terribly of allergy, and they sent him to Helgoland, an island north of Germany where there's no particular dust. Yeah. And he sat there, thought about it, and said, oh, what if quantum states don't need orbits to be described? Yeah. And he came up with what we call today matrix mechanics. Yeah? So the states of the quantum object, the observables, what we measure, are represented by matrices. Yeah? At that time, he didn't know anything about matrices. He was told later that he was playing with matrices. He didn't know. But anyway, he came up for the first time with a dynamical equation describing the behavior of quantum particles. Yeah? All we've seen before was just statics. Yeah? So he has for the first time a really dynamical equation. Now, where A could be the momentum, the position of something, and H is, of course, the energy of the system, the operator describing, or the matrix describing the energy of the system. Yeah? And his quotation is quite nice. Everything is vague and unclear to me, but it seems as if the electrons will no more move on orbits. Yeah? That's quite nice. Yeah? And 1932, 7 years later, Nobel Prize. Yeah? Because using his equation, we were not only able to solve the hydrogen atom spectrum, but also other forms of hydrogen and so on and so forth. Yeah? So this was really the beginning of quantum mechanics, yeah? Because there is a mechanical equation of motion. Yeah? Another gentleman, instead of going on an island, went skiing. Yeah, so that's why it's very important to take leave. Yeah, so don't forget to take leave if you want to do big things. Yeah? He came from another idea. He knew about the Broglie. Yeah, so the matter behaves like a wave, and if matter can behave like a wave, there must be a wave equation. Yeah, so he fiddled around until he found a wave equation for the for quantum mechanics, which is the so-called Schrödinger equation. And psi is the so-called wave function. Yeah? And he didn't like that because it's easier to manipulate mathematically than the Heisenberg equation, that even the Göttingen guys, Heisenberg and his friends, starting using it. As I said, the damn Göttingen physicists use my beautiful wave equation for calculating their shitty matrix electron. Yeah, so anyway, this is probably at the moment probably the most famous equation of quantum mechanics. The meaning of psi is still open for discussion. Yeah, interpretation of quantum mechanics. There are as many interpretations as there are physicists, probably. Yeah? But the most famous one is the Copenhagen interpretation. Yeah? And Max Born was fundamental in developing it, and he proposed that the meaning of the wave function is that its square is a probability. Yeah, so the probability of finding an electron something or of something happening in quantum mechanics is proportional to the square of the wave function. Yeah? The Copenhagen interpretation also assumes that once you measure your quantum state, the wave function collapses, yeah, and ends up in one of the eigenstates of whatever you're measuring with a probabilistic ratio. Yeah? What is also interesting, sorry, I just put it on this slide, although it doesn't really fit, is that I think Schrödinger himself and others showed that the Heisenberg formulation and the Schrödinger formulation are essentially identical. Yeah, they're completely equivalent. Yeah? So Born also 1945 took a little bit longer. It's like an afterthought, yeah, because it's difficult to prove an interpretation. Yeah? He also got his his Nobel Prize. So this is and this is the reason. These two slides are the reason why we are celebrating in 2025 the International Year of Quantum Science and Technology. So the first quantum revolution. What I want to show you now is that, I showed you early beginnings in 1900, 1905, the real revolution, 1925. Yeah, that's the year when the papers were published. Yeah? And then it took a long time, let's say 20 years until transistors were invented. Yeah? Even longer, 40 years until we had a laser and LEDs. Yeah? Even longer until we have a microprocessor. Yeah? Even longer until we have MRI. Yeah? And this is all things that can be explained just with those two equations. Yeah? So that the discovery of the Schrödinger and Heisenberg equation led essentially to our third industrial revolution. Now, that wouldn't be possible without quantum mechanics. Yeah? And as a matter of fact, we know that, for instance, more than 30% of the GDP of the US comes from those inventions there. Yeah? And this is the statistics of a few years ago, so maybe in the time it's much more. Yeah. So the laser is very interesting, yeah, because in 1917, Einstein proposed the physical phenomenon of stimulated emission. Yeah? He was interested in equilibrium properties of radiation and matter, yeah? And he discovered that without, there is of course emission if something is in excited state, there is absorption if I shine something with light, yeah? But in order to reach an equilibrium position, it was necessary to introduce theoretically stimulated emission. Yeah? So that was 1917. Yeah? He died in the 50s. Yeah? So long after he died, the laser was invented. Yeah? So this is again a sign that, from fundamental discovery while you're in holiday yeah, to a gadget that works, it can take a while. Yeah? So it was Myman who built the first working laser, yeah, with light. Yeah. Other people like Towns, Bazov, and Porco, they developed the theory of the laser and constructed masers, yeah, something similar to the laser in other wave frequencies. So this is one fundamental aspect of technology. The transistor, yeah, 1956, the Nobel Prize, yeah. This was necessary because you've probably all seen photos of the first computers, ENIAC, MANIAC in Los Alamos. Yeah? There were rooms like this filled with vacuum tubes. Yeah? And that is not really practical, yeah? Because they were not particularly efficient. They were prone to break and so on and so forth. Yeah? And if you had to find one that didn't work, it was really a problem. Yeah? Yeah? So they managed using quantum mechanics, yeah, and the band structure of semiconductors to invent this transistor that essentially controls the flow of electrons in matter. Yeah? So this was these three gentlemen, Shockley, Bardeen, and Brettain. Yeah? And keep in mind the guys in the middle, yeah? Because he got another Nobel Prize a few years later yeah, for superconductivity. Yeah? And superconductivity is something very interesting because it's a quantum effect that you can really see with the naked eye. Yeah? You can see the flow of electrons in one direction, the other direction with with your naked eye. And this again, it was observed in 1911, but the theory to explain it was only done in 1957. So another 40, 45 years later. Yeah? So it took quite a while. Yeah? And then, of course, many things that we do today with magnets, CERN, and so on and so forth, wouldn't be possible without superconductivity. The last example, so I'm just checking the time, of something that we use every day, yeah, are atomic clocks. Yeah, of course we don't have maybe an atomic clock in our watch or in our phone, but we use the GPS system. Yeah, and the synchronization of GPS systems only works because in every satellite there is an atomic clock. We can measure the time. Out of the time difference, we can find out where we are. Yeah? And so this, and you see that this the first atomic clock in 1955, quite a large object. Now they do atomic clock that like smaller than a coffee bean. Yeah? And probably, this is just from Wikipedia, probably there are even smaller ones. Yeah? So you could in principle have one in your phone. Yeah? Yeah? So this is very, and you see the precision is just unbelievable. Yeah? And our practical life wouldn't work without atomic clock, I think, these days. Even the SKA with all their dishes, yeah, they need to synchronize the timestamp of the various radio telescope with atomic clock, because if it's not, doesn't have that precision, it just doesn't work. Okay, let's move to the second quantum revolution, but let me have a sip of water first. Maybe you remember that I stopped the first quantum revolution in the 70s. Yeah, there's a reason for that. Yeah, and the reason is that it was only in the 80s that we started to develop the experimental ability to manipulate single quantum objects. Yeah. Until the 80s, nobody had ever seen a single ion. Yeah. There were only ensembles of ions, ensembles of atoms, yeah? Never a single one. Yeah? Nobody had ever seen a single photon. Yeah? That's changed in the 80s. Yeah? And that's why it is a real revolution, because up to then, speaking of atoms was just textbook crazy idea, and nobody had seen it. Yeah? And Hans Dehmelt was one of the guys who invented the ion trap and could actually see single ions, from the, you see, from the shape of the jumps, you can see whether the ion is in one state or in another. Yeah? And that was really a game changer, yeah, that we never had before. Yeah? Other people did what Dehmelt and his colleagues did for ions, did it for atoms and for light. Yeah, for instance, Serge Haroche develop technology so that you can really manipulate single particles of light and let them do things. Yeah. And together with his colleague Wineland, they got their Nobel Prize exactly for measuring and manipulating individual quantum systems. So this happened in the 80s, 90s, yeah? And we were not able to do it until that time. Yeah? This opened then, of course, a completely new dimension. Yeah? And that is that we were actually then able to use all the spooky properties of quantum mechanics that I didn't mention explicitly, like the superposition principle, entanglement, as resources to do stuff. Yeah? And this was acknowledged in 2022 with the Nobel Prize to Alan Aspect, Clauser, and Seilinger. Yeah? And what they were able to do essentially is that they proved what John Bell predicted. Yeah? That John Bell, who unfortunately died before the Nobel Prize, otherwise he probably would have been a strong candidate for that as well. Yeah? He described, found an equation that would have allowed you to show that entanglement is just real, and it's essentially the cause for the non-local properties of quantum mechanics. Yeah? And this gentleman showed that he was right. Yeah. So you see, they received their Nobel Prize for experiments with entangled photon, establishing the violation of Bell inequalities, and pioneering quantum information science. So the establishing the violation of Bell inequalities was fundamental because now we really know that our real world is non-local, yeah, because quantum mechanics has these non-local properties. And pioneering quantum information science because they use this, for instance, to do experimentally teleportation. Yeah, so we can teleport states of a quantum particle from one place to another, like in the science fiction movie. You can't just do it for us. It would be very practical. Yeah? So this was the beginning of quantum information science. And what we understand under quantum information science is essentially the merger of quantum mechanics and information science. Yeah. And quantum information science means that we now manipulate information. We store, process it, communicate information according to the laws of quantum physics. Yeah, we don't use anymore the transistor kind of physics. We just use all these fancy, spooky things of quantum mechanics. Yeah? And the quantum information science has essentially three branches. Quantum computing, quantum communication, yeah, the sharing of information, and quantum sensing and metrology. Yeah? And the big vision is, of course, one day to have a quantum internet, yeah, that just works with single photons and so on and so forth. Yeah. So what is, so this is the only slide with some mathematics. Huh? What is the, why is quantum information science so different from classical information science? Classical information, the classical bit can just be 0 and 1. Yeah, it's just, there is a current, there is no current, yeah? For instance. The quantum bit is also 0 and 1, but in fancy brackets, yeah? Which means that the 0 is just a vector that points from the center of a sphere to the North Pole, and the 1 by convention is a vector that points from the center of the sphere to the South. Yep. And the trick is that because of the laws of quantum mechanics, every point of that sphere is a legal quantum bit state. Yeah. So just optically, you see that many more things are possible with qubits that you can't do with bits. Yeah? And the promise of the second quantum revolution is that quantum metrology, quantum sensing will give us very, very precise measurement that could be relevant for climate change, for finding mines and things like that. Yeah? Quantum communication gives us really safe transport of data. Yeah? And safe means now safe because of physical principles. Yeah? It's not a mathematical algorithm that in principle you can hack if you have big enough computer power. Yeah? It's safe because of physical principles that so far we don't know how to break. Yeah? And quantum computing promises, for some cases, very fast data processing. Yeah? Let me maybe, okay, just to give you an example of how, for instance, secure communication works. Yeah? The only problem that you have in cryptography is to share a secret key. Yeah, because we know that if the key is as long as the message, there is no way anyone can uncipher the encrypt the message. Yeah? So the basic idea of quantum cryptography, and there is one protocol called BB84, yeah, is that we identify the 1 with the vertical polarization state of a photon, of a single photon, and 0 with the horizontal polarization. Yeah? So if Alice send the 1 photon, yeah, and Bob uses an analyzer that is also vertical and horizontal, with 100% probability, he also gets the 1. Yeah? But if Bob doesn't know what polarization basis Alice have chosen and he chooses the wrong one, yeah, then because of the rule of quantum mechanics, he could measure another state that corresponds to 0. Yeah, so he only gets 1 and 0 with 50-50 probability. Yeah, and out of this, you can develop a protocol to securely build a secret key. Yeah, because if an eavesdropper comes in between, it destroys that statistics, and then you immediately know that something went wrong. Yeah, okay, this is just the short version. Yeah? And back in Durban, in 2010, we developed a little quantum communication network between 4 provincial buildings. And in 2010, we also secured the communication between the Durban Stadium and the police station with a quantum key distribution link. Yeah? And for a little while, we were very famous. Yeah? Now, the problem is that in the 10 years ago, QKD just worked in optical fiber networks. Yeah? and it worked in optical fiber networks up to distances of the order of 100 kilometers, maybe 200 kilometers if you were very good and had very, very expensive equipment. Yeah? Mainly because the single photons then dissipate away. Yeah? So if you have this dream of a global communication network, you need to go via satellite. You need to connect metropolitan areas that are connected through optical fiber via satellite and reach any other part in the world. And for instance, China has various satellites that can do that for you. Yeah? And here in Stellenbosch, we are working with our Chinese colleagues to do a Stellenbosch China satellite link. Yeah? And hopefully soon Yazira will be able to tell you everything about it. Yeah. So this dream of the quantum internet is not that far away, yeah, because the bits and pieces are already there. Yeah? So let me speak a second about quantum computing. Quantum computing also started in the 80s. Yeah? At the same time when we started manipulating single quantum particles. Yeah? It was all together. Yeah? And Richard Feynman had the idea that, you know, our world at a fundamental level is quantum. So if we want to simulate it, assuming we had a quantum machine, it sounds like a good idea. Yeah? And then a few years later, David Deutsch in Oxford, he showed that in principle on paper, it is possible to build a universal quantum machine, yeah? Quantum computer. Yeah? So essentially he did what Turing did for the classical computer. He showed that in principle, you can build a universal quantum computer. Yeah? Okay, so that was an exotic idea. Exotic ideas. Yeah? 10 years later, Peter Shor showed that if you had such a quantum computer, you can come up with an algorithm that can factorize into prime numbers, yeah? Exponentially fast, better than classical. And that is really interesting because our security is based on the fact that it's easy to multiply two numbers, but it's not easy to find the two prime factors. Yeah? So that created a lot of interest. The same Peter Shor also came up with an algorithm for error correction. Yeah? You know, if you build a computer, every chip has errors, but there is built-in error correction to make sure that you get the right results. So we know also since the 1994, 1995, that if we had a quantum computer, there are algorithms to implement error correction. Yeah. Then, of course, many other algorithms were invented. Grover is an algorithm for search and so on and so forth. 1998, the first experimental quantum computer was built with NMR technology, just 2 qubits. Yeah? But it was a proof of experiment. Yeah? 2001, the Shor algorithm was the factorized 15, yeah? on some prototype of a quantum computer. Yeah? Around 10 years ago, probably IBM put the first quantum computer in the cloud. Sorry, I forgot to put it there. And 5 years ago, Google for the first time announced they reached quantum supremacy, that they could solve a problem on a quantum computer that a classical computer would require thousands of years to solve. Yeah? A few years later, people showed that you can actually do it on a classical computer as well. Yeah? But at least it was the beginning of a healthy competition. Yeah? But what is really very exciting is that in 2024, last year, yeah, almost in time for the international year, various companies, one of them being Atom Computing, another one being Quantinuum, they, they experimented with several logical qubits, so error-corrected qubits. Yeah? The standard quantum computer that you can have access at the moment is noisy. Yeah? There is no error correction. But now we know since last year, I think now they have up to 50 logical qubits. 50 logical qubits is a lot. Yeah? You can start really doing something, something serious. And that also means that maybe next year or this year we'll have 100 logical qubits. Yeah? And the power of quantum computer goes with 2 to the power of 100. Yeah? So that's a large number. Anyway, let me show you here. Just look at the 2 columns in the middle. Yeah, in the performance of the classical algorithm, where n is typically the complexity of the problem. You see there are lots of n's and so on and so forth. Yeah? In the quantum algorithm, you see lots of square roots and logs. Yeah? That's good. Yeah, because log mean there is an exponential speed up. Yeah? So you see we have classes of algorithms in which quantum computers can have an exponential speed up. Yeah? And that we hope is what will make a difference. Yeah? Even in machine learning algorithms, you see on the right quantum algorithm, again, lots of logs. Yeah? That's always good. Yeah, that means you can handle way more complex problem in a faster, shorter time. Yeah? It's still difficult to show, I mean, the idea of supremacy for now is dead, yeah? But there are still lots of people working on finding a practical solution for quantum computers, yeah, where we want to show that we can really solve. And, and a few years ago, I was involved with GESDA, which is the Geneva Science and Diplomacy Anticipator, in trying to come up with ideas of problems that quantum computers could be good at, yeah? And typically, they are simulation cases, yeah? Where you want to simulate quantum systems, you see, roughly from the chemistry environment, yeah? Or material science, yeah? For instance, to find carbon capture materials, yeah? Or you want to simulate how antibiotics diffuse into our wastewater and so on and so forth. Yeah, these are all problems that if you write down the equation, become very quickly very complicated. Yeah? Or this is also another very nice problem, yeah? To develop eco-friendly fertilizers. Yeah? You know, the industrial production of fertilizers only works at very high temperature, very high pressures. Yeah? But bacteria in the ground, they do it for free. But we don't know how they do it. We don't know how they do it. Yeah? So maybe with quantum computers, we will be able to simulate these chemical reactions at a quantum level to see what's going on. Vaccine distribution is also really complex, these logistical problems. This is also a very nice problem. Yeah? The sustainable food production. Yeah? This is very interesting because, you know, with climate change, what grows where is changing. Yeah? So it can be a very complex problem to know what you need to grow so that you can feed a population, yeah? In terms of calories and vitamins and so on and so forth. Yeah? So again, this can become very, very complicated. And I'm working with a colleague at the EPFL in Lausanne, where we try to hopefully prove that on quantum computers you can find some practical solution for this problem. But it's at the moment it's a hope. Yeah. In the announcement, I mentioned briefly also quantum effects in biology. Yeah, this is also something very interesting because we do some of that also in here in Stellenbosch. And this also started long ago in the 30s or in the 40s. Yeah? For instance, Erwin Schrödinger wrote a book, What is Life? Yeah? And, and he predicted that in order to explain things like evolution, yeah, we must have inside something that he called a quasi-periodic crystal. Yeah? Where is it? I think, yeah, aperiodic solid. That's some not periodic crystal. Yeah? Now we know it's DNA. Yeah, yeah. But he had already in the 40s a gut feeling for it. Yeah? And he developed this idea that quantum mechanics, because of the randomness and so on and so forth, might play a role in these processes. Yeah? Now we know that, it's not surprising. We're all made of stardust. Yeah? So we're all made of atoms and molecules. Yeah? So there must be some quantum inside. Yeah? A typical example, okay, I will mention that later, but the reason is very simple. Yeah? Quantum physics operates at a very fundamental level. Yeah? if light interacts with something, it can create a pair production, a radical pair production. This interacts with a magnetic field, for instance, yeah? And you could create a separation between a singlet and a triplet state. Yeah? That's basic quantum mechanics that can happen in us. Yeah? The singlet and the triplet state, however, they can have different chemical reactions. Yeah? And they can lead to other chemical products that are generated by this singlet and triplet. Yeah? The singlets and triplets can then lead to different biology. Yeah, because lots of chemical compounds form basic biological structures. Yeah? And the standard example, yeah, is indicated at the bottom there is bird migration. Yeah? We know, for instance, now that birds have these mechanisms somewhere in their beaks. They have cryptochromes that react with light, produce singlets and triplets when in contact with the magnetic field of the Earth, and they use this mechanism for orientation, for migration, for instance. Yeah? And we also know that there are some evolutionary advantage with certain isotopes or something, but these are just details. Yeah? But this is the most paradigmatic quantum effect in biology, probably. The migration mechanism of birds. Even, a few years ago, we were all scared of COVID, and everybody tried to do something to alleviate the impact of COVID. And so we came up with a model where quantum tunneling could enhance or suppress the transmission of the COVID virus in a body. Yeah? And that's, again, a typical quantum mechanical effect. Yeah? It's just theory for now. Yeah. But coming slowly to a conclusion, and later you're welcome to ask question if the chair allows. Yeah? And the conclusion are just random thoughts. Yeah? One is this one, which is really critical. Yeah, we spoke a lot of quantum computing. Yeah, and I told you that quantum computing poses a threat to our standard encryption methods like RSA. Yeah. So people say, okay, but quantum computers, we don't have them maybe in 10 years, maybe in 20 years, maybe next year. Yeah? But there is reason to take it very seriously. Yeah, for exactly for that equation. Yeah? That is named after Michele Mosca, who is also a theorist based in Canada. And his reasoning is the following one. Yeah? Let's assume you have a quantum threat time, yeah? Which is your estimation when quantum computing will be able to hack, let's say, RSA for 2,000 qubits, 2,000 bits. Yeah? Let's assume it's 10 years. Yeah? So after 10 years, you have a problem. Yeah? How much time do you need to migrate your security to post-quantum cryptography? So to cryptographic protocols that are resistant to quantum computer attacks. Yeah? Let's assume that's 7 years. Yeah? Then you see, and then the second variable, the third variable is, what is the shelf time of your secret? How long do you want your secret to be secret? Yeah? Because let's assume you encrypt your stuff with standard RSA. Yeah? The lock is locked in your web browser. Yeah? I can still download those data encrypted. I can't read them, but it's very easy to bend the fiber and read what comes out. Yeah? I still can't read it literally, but I can steal it without you noticing it. That's easy. But when I have a quantum computer, I go back to the data that I stole, yeah, and decrypt them, yeah, and read your secrets. So if you want your secret to be secure for a certain time, you have to start getting ready now. Yeah, you need to gauge your migration time up accordingly. So some of you, maybe not me, I don't have many secrets, but some of you who might have secrets, have to start thinking now, because it's easy to steal your encrypted information, and the moment people have a quantum computer, they can read everything. So this is something, and migrating to post-quantum cryptography is not something that you do overnight. It will take some time. This migration to quantum cryptography, now becoming a little bit technical, is very important because it will accelerate quantum computing research. Because the moment you develop post-quantum cryptographic protocols, you need to make sure that the quantum computer won't be able to hack it. And you will have only the proof when it's hacked. So post-quantum cryptography, the adoption of post-quantum cryptography, and there are already standards. For instance, I think on Google, you can already encrypt your stuff with post-quantum cryptography. I think Apple does it as well. It means that quantum computers are taken seriously. And there will always be this interplay within encrypting something and wanting to decrypt it in illegal ways. So post-quantum cryptography is something very important and will be very good for quantum computing. Now, where do we stay in South Africa? If you go on the Amazon AWS, you have access to 4 or 5 different types of quantum computers in the cloud. Google has a few more. In the UK, there is since a year a quantum computing center, and they have 12 different quantum computers that people can use. We have 0. So we have lots of catch up to do. We can access them in the cloud. But the problem is not yet, but could be. There are already export controls on quantum computing hardware and access. So you won't be able just to pull out your credit card and buy one. People will check what intentions you have. And from export controls to export not possible anymore. It can be a small step. So we really need to apply our mind how we deal with it. So what is then the path to quantum readiness? In South Africa, we have maybe 10 years after many other countries, a quantum technology initiative, which gives us funding for students, for research, for access to quantum computing hardware, and so on and so forth. We have partnered, you see there, Q South Africa with QWord, which is also a non-profit organization that wants to promote the use of quantum computers and trains in quantum computing. And every year, I think Omid is here, he's our coordinator. He organizes lots of workshops and schools to teach quantum computing at all levels. Our CHPC is the national institute that gives us access to quantum computing in the cloud. And we also partnered with OQI, the Open Quantum Institute, which is an initiative at CERN set up recently to, in principle, offer quantum computing access for free to the world. But we will see how that goes. But so this is essentially the ecosystem. And as a last slide, I mentioned lots of Nobel Prize winners. So I had the idea, let's check how many Nobel Prizes were linked to quantum anything. And if you, this is not audited, so I might miss some, or I might be counted twice. But there were around 40 over the years. See, in 1910, 1923, 1940, 1970 were a little bit problem decades. But on average, almost every 2.5 years, there is a Nobel Prize in quantum something. So if South Africa wants a quantum Nobel Prize, this is where we should put our funding, because it probably is the easiest disciplines to pick. In medicine and physiology, there are lots of disciplines. The Nobel Prize is for physics, so there are lots of disciplines in physics. But I think quantum is the again, not audited, but I think is the leading one. Okay, so that's it from my side. Thank you very much.
Thank you very much, Prof. Francesco, for an
Pleasure.
excellent talk. Any good question?
Bad questions also? Okay.
Yeah.
So let's consider a scenario where we don't have funding problem.
Yes.
What would it take for South Africa to become quickly one of the world leading quantum countries?
2.5 years.
I'm asking what we'll have to do to achieve that.
You know, it essentially what more or less what I indicated here. Yeah, we need education and awareness. You give me the funding. We need to educate a quantum workforce that we
More
don't.
concrete, more
sorry?
concretely. What would be the plan? More concretely.
Like what we want to do here, set up a master's in quantum technology or in quantum computing. Yeah. Maybe one day have a quantum faculty. No, I don't know, but at least having a formal degree, yeah, that people can be trained as quantum scientists and quantum engineers. Yeah.
Undergraduate or postgraduate?
I would start at postgraduate, and then depending, you could start earlier. Yeah.
Thank you.
Question. When you store information with qubits,
Yes.
isn't there a risk that when you measure what you store there, you change
Yes.
with your own measurement?
That's why it's difficult to build quantum memories. Yeah.
Okay.
Yeah. Or quantum RAM. It's also difficult. Yeah.
Is it easy for me to understand like the idea of how you can
Yeah, you need to
overtake this
develop a
problem?
quantum state that is long lasting and resistant to noise. Yeah? And you'll be able to read it without disturbing it too much. So it's not an easy problem. People are working on it. It's not an easy problem. Yeah? Related to this, the other technical challenge is quantum repeaters. Yeah? You want then that quantum state be able to repeat it in many different places. Yeah? So that's related to the quantum memory problem. Yeah?
Thank you.
Any other question? Just a quick one. In your work for quantum science, did you apply any work in finance?
Not yet, but I have a new student that wants to do exactly that. Yeah.
Okay.
So
I
we will.
think it will be interesting
Yeah,
to
no.
look at this theory into application into quantitative finance.
Yeah, that will be very nice.
Yeah.
Well, that works. I wanted to ask, like you said before, would a system like that where you make sure that something doesn't suddenly change be similar to how, like, I know in information systems, there's already a thing of like, how much noise can there be before before you have no idea whether or not you got the original message or not, where you, even with normal bits that just have two states, you have somewhat of a probability that something changes somewhere. Is it similar? Does it work similar to that?
That's similar. That's why I mentioned earlier that most of the quantum computing hardware that we have is noisy, yeah, in the sense that there is no built-in error correction, yeah, and that increases, of course, the probability of errors, yeah. And the technical challenge for error correction is that you need many more qubits to implement the error correction codes. Yeah? And most hardware companies don't have them, don't have them yet. Yeah. So in principle, we know how to do error correction. It's an engineering problem. That's why I said we need quantum theorists and quantum experimentalists and quantum engineers, yeah, to get there. Yeah.
Sorry, I have another question. Is
Please.
it possible to like make a computer that uses has some components that do classical computing and some do quantum computing? I know there would be a significant speed difference, but
No, that's a very nice question. In fact, the most successful algorithms so far are hybrid, yeah, in the sense that they have a quantum component and a classical component. For instance, there are a class of algorithms called variational quantum algorithms, yeah, where you run something on the quantum computer, you measure some kind of loss function, you minimize that on a classical computer, and you go back to your quantum computer. Yeah, that's a very popular strategy. Yeah? And in future, it probably it wouldn't happen that you have a quantum processor in your laptop. That probably wouldn't make sense because you can type only so fast. But there will be always a hybrid environment, where you have classical computers, supercomputers, quantum computers. Like now you have CPUs, GPUs, you will also have the QPU. And depending on the problem that you have, you will use whatever is needed to achieve your goals.
Any other question from online audience?
Okay, we have our first question here is when we look at atomic theory's improvement through years and its late acceptance, it seems maybe we can come to a consensus on also string theory one day. What is Prof. Petruccione's idea about that? I'm going to group this with another question from Anna Schuyfer that says, what do you think will be the most exciting quantum advancement in the near future? And then if you finish answering these, if you want, I'll give the others.
I mean, the first question about the string theory, I'm not sure whether they will be useful in the quantum computing context because of usually they are useful at high energies. So to building a quantum computer, they might not so be useful. No? Some of the mathematics of string, they might be useful. So some people want to build topological quantum computers, mainly because topological qubits are more resistant to noise than other qubits. There might be some relationship there, but I think at the moment it's two disjoint things. What was the second question?
The second one from Anna Schuyfer. What do you think will be the most exciting quantum advancement in the near future?
Yeah, one we already experiencing now, that we are moving from noisy qubits from physical qubit to logical qubits. Because once we have quantum computers only built with logical qubits, all the nonsense of noise is gone. Now we can really use the fault-tolerant quantum algorithms that we know are out there that will give us exponential speed up to solve certain problems. The other advances are in sensing and communication. To have a quantum internet sounds quite fancy to me. And we're also almost there because we know how to do it in fiber, we know now how to do it in satellite. It's becoming just an engineering and scaling up problem. It's not a principal problem anymore. What I would find even more fascinating, and I only mentioned it briefly at the end with quantum effects in biology, we all would like to know how the brain works. And I'm sure there are quantum effects in the brain as well. The question is whether they are relevant for us functioning. Our brain is quite slow. It operates on the signal processing. It's on time scale of seconds, not on nano, pico, blah, blah, blah second. So there are lots of things that we don't understand. And it will be very nice to find out whether there are effects there. One very exciting example is that we all know that we can use, for instance, noble gases like xenon as anesthetics. So I give you xenon, I knock you out. But if I give you an isotope of xenon, in which there is maybe one neutron more, it doesn't work. And that's just one spin. And nobody really knows why. But experiments are made, so people know. So there are lots of things that can be very exciting.
A quick question here.
Please.
Professor, a few years ago, the term of the time was singularity. So I'm speaking here as not an expert in computing, but my understanding of that was that it would be the moment that computing supersedes human abilities and finds the answer to everything, to medicine, to astrophysics, etc., the origins of life, etc., etc. So is quantum computing bringing us closer to that point, or is that a fool's gold?
The answer is probably not yet. The contribution of quantum computing can be on various aspects. One is that, in order to reach this general intelligence, at the moment, people just scale up big clusters of GPUs, yeah? And who pays the electricity bill, yeah? You know, the Googles of this world, Microsoft, they're speaking of building or buying their own nuclear power station just to run their data centers, yeah? So that's not exactly sustainable, yeah? The big advantage of quantum computers is that they use much less electricity, yeah? So if we had same algorithms running on quantum computers, the electricity bill would be a little bit lower, yeah? Yeah, at the moment, you know, we don't really know how to do the large language model on quantum computers. The main reason is that, you know, if you want to analyze big data sets, you need to feed them into your computer. Yeah? And feeding data into a quantum computer is orders of magnitude slower than feeding data into a GPU. Yeah? Many, many orders of magnitude. So that even if the quantum computer is a little bit fast, yeah, and it takes you a week to upload the data, yeah, the advantage might be lost. Yeah? This is at the moment. It doesn't mean that maybe one of you tomorrow morning wakes up and finds the solution how to do it much faster. Yeah? But at the moment, that is a problem. Yeah? That's why I stressed simulation as examples where we will have a quantum advantage or a practical use, because those are problems with few parameters, but need of large computational power. Yeah? And not much input output. Yeah? At the moment, input output is very, very slow.
Yeah, Renee?
We have more than 60 people online, and we have like 6 more questions to do. And I see it's like 4 minutes past 5. Can I ask?
Yeah.
It's
If
a quick one,
they're not too
and,
philosophical.
Okay. Okay. Rabelani says, very informative, Prof. Thank you very much. Can't wait to apply quantum computing to bioinformatics. Then Lerotori Liu says, apparently China has quantum computers available for sale to South Africa. Which of these can go to South Africa for and based where? Then Sia Bulela says, good day, Prof. Petruccione. If you were to start learning quantum mechanics from scratch as a complete beginner today, how would you structure your learning process? Which key topics, mathematical foundations, and practical exercises would you focus on? This is a long question. Yeah,
Let me start with that. I would just ask ChatGPT. Yeah. Yeah.
Okay, then we have another comment. Could you please comment on the status of quantum science and technology in Africa, especially the scientific collaboration? 2 more, what interpretation?
No, let's stop there a second. I mean, many years ago, we started here, okay, I was in Durban, a conference series called Quantum Africa. And that was the idea to bring together the quantum community across the African continent. Yeah? And this year there will be one edition in Morocco. Yeah. So if you want to interact with other African quantum guys, yeah, there will be a Quantum Africa conference, I think in September in Morocco. Yeah. But having said that, there is a quantum activities in the southern part of Africa. There's quantum activity in the northern part of Africa, and a little bit in between. Yeah. So there is really a need to intensify the training and on so forth of quantum computing and the other quantum technologies, yeah, all over Africa, yeah, because you know, countries like South Korea uplifted their economy, investing heavily in semiconductors. Yeah, that was first quantum revolution. Yeah, now we are in the second. If we miss this train again, yeah, it will take a while until there is a third quantum revolution. Yeah, yeah. So it's really important that we invest and that we don't miss the opportunity that are still there. Yeah?
Okay, our last 2 comments. What interpretation of quantum theory does Prof find most appealing? And the last one, my question is similar to the one of Sia Bolela. Which sector will the course dominating mostly? Financial sector, engineering, health? And he's basically saying this is a very interesting topic. Thank you. We had more than 60 people online, so thank you. To our
the interpretation question I will ask after we had a glass of wine outside. Because then we will be here until tomorrow. Yeah? What was the last question? Sorry. Which application? You know, the answer is probably we don't know. Nobody has found yet a case where quantum computing surpasses the ability of a classical computer. Yeah. So it will be up to the creativity of people to find the use cases that, there are strong candidates, yeah, but nobody has explicitly shown supremacy, advantage, practicality, utility, however you want to call it. Yeah. So it's it's an open field to explore. Yeah.
No, thank you, guys. Help me to thank Professor Francesco Petruccione for an excellent talk.
Thank you. Pleasure.
Thank you to our online audience, the in-person audience. So we have some